Hello everyone, and welcome back to a new video in programming the finite element method using MATLAB. In this video, we are going to continue our efforts towards calculating the matrices necessary for assembling the global stiffness matrix. In the last video, we did a massive chunk of coding in the fembar spring, and there was one thing about the initialized local equivalent nodal loads. I just do it very quickly at the start of this video, and then we're gonna jump into the fembar beam and see how the stiffness matrix looks. Now, before I jump into the stiffness matrix and how it looks, I want to remind you that there are two playlists where these videos are part of. One of them is called the Fem playlist, where I explain the theory before I explain the programming of that thing, and the other one is pure programming. Furthermore, if you are a channel member, then you would have access to the entire source code. However, if you are not a channel member, then don't worry, because you can actually write along and you would have the exact same code as I have. So with that being said, and without further ado, sit back, relax, and enjoy the show. Okay, now first things first, let's deal with the initialized local equivalent nodal load matrix. So that's not really hard. I'm gonna basically go here and say object dot, there we go, local, right? So local equivalent nodal stuff. So here, local equivalent nodal load matrix. I called it force, it seems, in there. I think I wanted to call it load because load is more accurate. So here I'll call this nodal load, and you can see once again the utility of inheritance, because now I need to change two files instead of one. This could escalate out of control if you have a bigger project. So here, this is once again telltale signs where we should be using inheritance. Equivalent nodal load matrix. So here this is going to be equal to zeros. Let's leave the rows as being degrees of freedom and the columns as being the load cases. So here, 2 multiplied by 6 or 12. This is once again magic numbers. I don't like them, but I think I can let it slide because you know exactly that we have 12 degrees of freedom, so that's not a big deal. Here I have number load cases, and that's that. So we now have defined or initialized our local equivalent node matrix in fembar beam and also in fembar spring. And by the way, this brings the fembar spring for now to a close. There is still post-processing calculations will happen here, but for now, for the fem calculations, we have accomplished fembar spring officially by that. However, we're still stuck with the fembar beam, specifically with the stiffness matrix of that thing. Now, to be able to calculate the stiffness matrix, you could use shape functions and go the longer integration path, or you could just open Daryl L. Logan's book and pick out the stiffness matrix from that book. I need to test it before I can basically release it to the public. So okay, let's just quickly open, I'm just opening the book right now. If you have Daryl L. Logan's book, the 4th edition, on page 257, he talks about the beam element arbitrarily oriented in space, and in his equation 5.5.3, he gives you the stiffness matrix of that beam. And I'm gonna use the stiffness matrix to basically write it here. So I'm basically opening Daryl L. Logan's book and picking out the stiffness matrix to write it here. So, okay, first of all, I don't want to keep saying object dot, it takes too much time and there is so much to calculate. I basically declare a variable called k local, and this is going to equal 0, or just k small, and this is going to equal zeros of 12, 12. 12, 12 because I know that I have 2 nodes, and I know that I have 12 degrees of freedom. Now here, the big matrix needs the area, needs the elastic modulus, needs the length of the beam, needs the Ix of the beam, it's called J by the way, in the equation, needs the shear modulus. Oh, that's bad news, because I haven't programmed the shear modulus in my material. I need to modify this. Let's rearrange them. So it needs something called the section characteristics, it needs something called the material characteristics, and it needs something called the geometrical characteristics. Now here, I am very sad because I forgot to define G in my material. The area here is going to equal corresponding object dot corresponding str_line dot section dot ax, because it's called the x in the str section. Let me just check if I called it that way. So where is the str section? It's been ages since I have done that. str section, there it is. Yeah, I call it AX. Now, IX is still incorrect, by the way, because I told you there is a crazier calculation, will be equal to object.corresponding strline.material.g. This L is going to equal the length, object.length, because I think I have it, right? Do I have it? Yes. And now I should start filling it in. However, it won't work. It won't work because material.j doesn't exist. Allow me to show you this in its all glory. I'll run and see what happens. Boom, G doesn't exist. Let's take a look. Unable to perform assignment course size 77. Oh, this is even worse. This is even worse. I will first of all program the FemBar beam, and I will keep the next video for all those errors. So K of 1 and 1, that's the axial, equals, and I really highly recommend that you open on your other screen, if you have one, on your mobile phone, you open the Daryl L. Logan book and see me doing this in action. Alright, so I just basically dished out the entire stiffness matrix of Daryl L. Logan's book. To be honest, I might need to debug this. I'm pretty sure I must have made a mistake somewhere. Now we just need to say object.local stiffness matrix equals K, and this would end our video today because we have defined the local stiffness matrix of a beam. Now, of course, there is a ton of errors that need to be debugging. I will do a micro debugging session in the next video, but for now, I will stop it here and basically give you my usual outro. So yeah, that's everything I wanted to talk about today. I hope you enjoyed. And in the end, I want to give an incomplete sized shout out to my dear channel members in the contributor level and the helper level whose names are going to be shown on the screen. I want to thank them from the bottom of my heart, as their support to the channel is priceless to me and enables me to provide you with videos hopefully on time and with a certain quality I try to achieve, and for that I am forever thankful. In the end, I hope that you enjoyed the video and you found it beneficial. If you have enjoyed it, then please consider liking, sharing, subscribing and commenting, especially subscribing because it helps increase the reach of my channel. As per usual, this is the Civil Engineering Essentials channel. I will catch you in the next video. Bye bye.